Hello, everyone. Welcome. My name is Chang. So far, we learned ROS, SLAM, manipulation, and planning. Today, we will study computer vision to see the world. Camera is used to see the objects and obstacles ahead of or surrounding the robot. Of course, computer vision is not all of AI. AI is a lot more than just that. It needs to see, it needs to hear, and it needs to have basic knowledge about the world. All of this is needed for having intelligence. I am going to be talking about object detection. Who has heard of object detection? Who has heard of YOLO? This is pretty much going to be a review, I guess. Object detection is used when you want to detect instances of semantic objects that the model was trained on prior to its use. Here we see three pedestrians crossing the street. On the right-hand side, we also see cars. In order to detect people and cars, an algorithm was trained using data to detect humans and vehicles. Detecting objects is an essential element for building physical AI, and there are many algorithms to perform object detection. There is YOLO, faster RCNN, and many other detection algorithms. Anyone here know the difference between YOLO and faster RCNN? I can give you a hint. YOLO is considered a one-stage detector, and faster RCNN is a two-stage detector. Faster RCNN performs object detection by first finding out regions where there might be predefined objects. It has a network that finds region proposals, and from that region, it does classification. So it is a two-stage process. YOLO is a one-stage detector. It finds the region and also classifies it simultaneously. This slide is about image segmentation. I think image segmentation gives all the information about our surroundings. Who has heard of image segmentation? Image segmentation is when, given an image shown here, it tries to classify each pixel as one of the objects. There are various types of segmentation algorithms. You just label the predefined classes so you can tell exactly how many cars there are in this image. I show you this because I think this provides a much better understanding of the surroundings. But for simplicity, I am going to focus on object detection. There are different ways to understand the world, such as by sound or the distance of objects, but let us focus on object detection and segmentation. There are pros and cons when comparing them. Object detection requires much less computation than segmentation for an obvious reason. In segmentation, we are trying to label all of the pixels, essentially. In object detection, you are just trying to find where your object is and classify it. Object detection obviously provides less detailed information compared to segmentation. We are going to focus on YOLO, which is computationally cheap and fairly accurate. How much computation does it require to do detection versus segmentation? It takes 30 gigaflops for YOLO, and for segmentation, it is 33 times higher. I think the robot that we have can do about a teraflop of operations. YOLO can do 45 frames of detection per second, which requires 1.4 teraflops, while segmentation requires much more, around 58 teraflops. This slide shows the inference cost and the hardware computations required for YOLO versus YOSO, which is a segmentation algorithm. You can also run your object detector with an LLM like ChatGPT loaded onto this robot to enhance the performance. I think we all had ROS. I am sure that you are familiar with this notion. ROS is built upon a thing called packages. The package has nodes. A node is like a program. A topic is the communication between the nodes, and you are sending messages between these nodes. Why am I showing you this for object detection? Why is this very important? You have a camera which receives images, and those images have to be sent to the YOLO program. The YOLO program processes the image and produces the output to send it out. So YOLO acts as a node. So there is a camera node which takes RGB images. It sends them out to the YOLO node, and the YOLO node performs the detection. Let us talk about what YOLO is actually doing. Does anybody here know how YOLO operates? Let us assume that the image contains one object, like a dog, a person, or a chair. How would you detect this object? How do you know whether there is this object, or how do you classify that? There is an image, and you have one of the many objects in the image. What will be an algorithm to tell you what is in the image? You might suggest that we can group similar pixels together using clustering. Yes, clustering is one way. We can train the model to classify images of dogs. However, dogs come in many different sizes and forms. They are all four-legged, but a dog could be standing up or doing various tricks. How would you classify a picture of a dog? The point is that you want to extract information that is distinguishable from other classes. Let us say I am trying to distinguish between a cat and a dog. A cat could be doing a lot of different things like standing up, running, or jumping, and a dog could be doing that too. There are different types of cats and different types of dogs. What you want to do is extract features. That feature might be the length of the body with respect to the length of the dog's leg. That might be one feature. You may get an average of all the different types of dogs doing different things. And you do that for cats as well. You have these certain features, and then for a particular dog or cat, you extract that feature and see whether it is closer to a dog or to a cat. In order to extract that information, how would we then classify it? You might ask, how do we know what to select? And how do we extract a great feature that would cover different types of dogs doing different motions and different cats? That is a very good question. What would be a way to extract that good feature? Let me just tell you, you take the image. You have a whole bunch of images of dogs and cats, maybe 10,000. Then you have a function. This function is malleable, meaning that you can change its parameters. You take a function and you set it randomly. You apply that function to each of those images that you have, and that function is going to give you some output. From that output, you're going to have a simple classifier that would tell you whether it is a dog or a cat. If the classifier is not predicting correctly, you use feedback and modify the parameters of the function until it gives you a good feature to accurately predict a cat. That is what we are doing right now. That is the state of AI right now. And what is that function we use? We use deep learning, a deep neural network, or a deep convolutional neural network. We apply the deep neural network, or CNN, to produce some output, and based on that output, we try to predict the classes. If we cannot, then we modify the function and we keep on doing that. That is for one image and one object. Are we always classifying one object in an image? We have multiple objects. YOLO is an object detector that tells you where the objects are and what they are for multiple objects. And how does it do it? It tells you the center coordinate of the object and the width and height of the box that will contain the object. And finally, it will spit out the probabilities of the different classes. This is what YOLO does. If there are 3 cups in the image, multiple objects, it is able to detect them, and it is very efficient to do. It takes the image and produces the class probabilities and the bounding boxes of the objects. Now let us move into YOLO. YOLO stands for You Only Look Once. The name is actually a very good summary of the main idea. Instead of looking at an image many times or first searching for possible object regions and then classifying them, YOLO tries to predict everything in one forward pass of a neural network. The original YOLO paper was introduced by Joseph Redmond and his colleagues in 2015 under the title, "You Only Look Once: Unified Real-Time Object Detection." At that time, this was a very important shift in object detection because the method was designed not only to be accurate, but also to be fast enough for real-time use. In object detection, the model has to answer two questions at the same time. First, what objects are present in the image? And second, where are they located? YOLO handles both questions together. It predicts the class label, such as person, car, dog, or traffic light, and it also predicts the bounding box around each object. This is why YOLO is called a one-stage detector. The model directly maps an input image to detection results. There is no separate region proposal stage. This unified design is one of the main reasons why YOLO became so popular for real-time applications, including robotics, autonomous driving, surveillance, and embedded AI systems. Since YOLO V1, many improved versions have been proposed. The details have changed a lot over time, but the central philosophy has remained similar: fast, unified, and practical object detection in a single pass. On this slide, we compare two-stage detectors and one-stage detectors. Let us start with the two-stage detector. A typical example is FastRCNN. In this kind of approach, the system first searches for candidate object regions. This first stage is called object region proposal. For example, selective search can group similar pixels and propose regions that may contain objects. Then, in the second stage, a convolutional neural network classifies each proposed region and refines the bounding box. So the two-stage detector separates the problem into two steps. First, find possible object locations. Second, classify and adjust them. This can be accurate, but it is usually slow because the system has to process many proposed regions. YOLO takes a different approach. YOLO is a one-stage detector. It does not explicitly generate region proposals first. Instead, the input image goes through convolutional layers, features are extracted, and the network directly predicts object classes and bounding boxes in one pass. The table at the bottom shows the trade-off clearly. FastRCNN has a higher MAP score in this example, around 70, while YOLO V1 has a lower MAP, around 63.4. So YOLO V1 sacrifices some accuracy. However, the speed difference is huge. FastRCNN runs at about 0.5 frames per second, while YOLO V1 runs at about 45 frames per second. This is the key point. YOLO was not originally designed to win only on accuracy. It was designed to make object detection practical in real-time settings. For robotics and physical AI, this speed is extremely important because the robot must perceive the environment and react quickly. Now, let us talk about why YOLO is useful in real applications. There are three important advantages. First, YOLO is fast. Even the first version of YOLO could run at roughly 45 frames per second, which is already suitable for real-time video processing. Second, YOLO is unified. It uses a single neural network without a separate proposal generation step. Third, YOLO is versatile. The same general idea can be applied to many environments such as autonomous driving, robotics, video surveillance, and augmented or virtual reality. For self-driving cars, YOLO can detect pedestrians, vehicles, traffic lights, and other important objects on the road. In this case, latency is critical. A delayed detection can lead to a delayed decision for human pose estimation. YOLO-style models can also predict key points of human body parts. In the image on the right, we can see the estimated skeleton of a person. This is useful for human behavior understanding, sports analysis, and human-robot interaction. In robotics, object detection can be used for grasping, manipulation, and navigation. For example, before a robot arm picks up an object, the robot first needs to detect where the object is in the image. For video surveillance, YOLO can track objects in real time, such as people, vehicles, or unusual events. And in AR and VR, object detection helps the system understand the surrounding environment and place virtual content in a meaningful way. So the main message of this slide is that YOLO is not just a model architecture. It is a practical detection framework that connects computer vision algorithms to real-world systems. From this slide, we focus on YOLO V8. YOLO V8 follows the same high-level idea as earlier YOLO models. It performs object detection in a single forward pass. The input image is passed through the model, and the output is a set of detected objects with class labels and bounding boxes. The pipeline can be understood in 4 parts: backbone, neck, head, and post-processing. The backbone is responsible for feature extraction. It takes the raw image and converts it into hierarchical visual features. Early layers usually capture low-level patterns, such as edges, colors, and textures. Deeper layers capture more semantic patterns, such as object parts or object-level information. The neck performs multi-scale feature fusion. This is important because objects can appear at very different sizes. A small cat and a large dog should both be detected correctly. The neck combines information from different feature levels so that the detector can handle both small and large objects. The head is the prediction part. It predicts class scores and bounding boxes from the fused feature maps. In YOLO V8, different heads can also be used for other tasks, such as segmentation or pose estimation. Finally, post-processing filters the raw predictions. The model initially produces many candidate boxes. Some of them are low confidence, and some of them overlap heavily. So confidence filtering and non-maximum suppression are applied to produce the final detection results. When looking at the diagram, think of YOLO V8 as a pipeline that gradually transforms an image into useful predictions: image, features, fused features, dense predictions, and final detections. Let us look more closely at the backbone of YOLO V8. The backbone is the feature extraction module. Its role is to convert the input image into feature maps that are useful for detection. A raw RGB image is just a grid of pixel values. The model needs to transform these pixels into higher-level representations. In the early layers, convolutional operations capture local patterns, such as edges and simple textures. As we go deeper into the network, the spatial resolution becomes smaller, but the channel dimension becomes larger. This means that the model keeps less detailed spatial information, but stores richer semantic information in each feature location. For example, C1 can be thought of as a feature map with about 1/2 of the original image resolution. C2 has about 1/4 of the original resolution, and the resolution continues to decrease as the network goes deeper. At the same time, the number of channels increases, allowing the network to represent more complex visual concepts. YOLO V8 uses C2F blocks to improve feature representation while keeping computation efficient. These blocks help information and gradients flow through the network effectively, which is important for training deep models. The main outputs of the backbone are C3, C4, and C5. These are feature maps at different scales. C3 has relatively higher spatial resolution and is useful for smaller objects. C5 has lower spatial resolution but stronger semantic information, which is useful for larger or more abstract objects. So the backbone does not directly produce the final boxes. Instead, it prepares multi-level visual features that the later parts of the detector can use. Next, we discuss the neck of YOLO V8, which performs multi-scale feature fusion. Why do we need this part? The reason is that object detection has to handle objects of many different sizes. A small object may require high-resolution spatial information. A large object may require stronger semantic information from deeper layers. If we only use one feature level, the detector may miss either small objects or large objects. The neck combines shallow and deep features. In this slide, the process is divided into two directions, FPN and PAN. FPN stands for Feature Pyramid Network. It uses a top-down pathway. This means that high-level semantic information from deeper layers is passed down to shallower feature maps. In simple terms, deeper layers know more about what the object is, and FPN helps deliver this semantic information to feature maps with better spatial resolution. PAN stands for Path Aggregation Network. It uses a bottom-up pathway. This direction sends lower-level localization information back toward deeper feature maps. In simple terms, shallower layers know more about where things are, and PAN helps preserve this localization information. Together, FPN and PAN allow the network to combine what information and where information across different scales. The final outputs of the neck are P3, P4, and P5. These are multi-scale feature maps used by the detection head. P3 is usually more useful for small objects, P4 for medium objects, and P5 for large objects. The key idea is that YOLO V8 does not rely on a single representation. It builds a multi-scale representation so that detection can be robust across object sizes. Now we move to the YOLO V8 detection head. The detection head takes the multi-scale feature maps, P3, P4, and P5, and produces predictions. These predictions include object class scores and bounding box coordinates. The first important concept here is dense prediction. Dense prediction means that the model predicts at many locations on the feature maps. For every spatial location in P3, P4, and P5, the head checks whether an object is likely to exist there, what class it may belong to, and where the bounding box should be. The second concept is anchor-free prediction. Earlier object detectors often used predefined anchor boxes. These anchors were hand-designed boxes with different sizes and aspect ratios. The model then adjusted these anchors to match the objects. YOLO V8 instead follows an anchor-free design, so it directly predicts bounding boxes without relying on predefined anchor boxes. The third concept is the decoupled head. In YOLO V8, classification and box regression are predicted by separate branches. This is useful because recognizing an object category and estimating a precise box are related, but not exactly the same task. A classification focuses on what the object is. Regression focuses on where the object is. On the right side of the slide, the classification output has the shape H by W by C, where C is the number of object classes. The regression output has the shape H by W by 4, corresponding to the box parameters. So the detection head converts each multi-scale feature map into many candidate predictions. These predictions are not yet the final answer. They still need to be filtered in the post-processing stage. After the detection head, YOLO V8 performs post-processing. This step is necessary because the raw output of the detection head usually contains many candidate boxes. Some boxes have low confidence, and some boxes describe the same object multiple times. If we directly use all of them, the result would be messy and redundant. The first step is confidence filtering. Each predicted box has a confidence score or a class score that indicates how reliable the prediction is. Predictions with very low confidence are removed. This reduces noise and keeps only boxes that are likely to correspond to real objects. However, confidence filtering alone is not enough. The model may still predict several high-confidence boxes around the same object. For example, for one dog, the model might generate 5 or 10 slightly different boxes. They may all be reasonable, but we only want one final box for that dog. This is where non-maximum suppression, or NMS, is used. NMS compares overlapping boxes and keeps the most confident one while suppressing the others. So the full post-processing pipeline is simple but important. The detection head produces many candidates. Confidence filtering removes weak predictions. NMS removes duplicate predictions. The remaining boxes become the final detection results. In real-time systems, post-processing also has to be efficient. Even if the neural network is fast, slow post-processing can reduce the overall frame rate. That is why object detection systems must be designed as a complete pipeline, not just as a neural network. Let us examine non-maximum suppression more carefully. During prediction, an object detector often produces multiple boxes for the same object. In the left image, we can see many overlapping boxes around the dog and the cat. This happens because nearby feature map locations may all predict similar objects, and multi-scale features can also produce overlapping predictions. The goal of NMS is to remove these duplicates and keep only the best prediction for each object. The procedure is iterative. First, NMS selects the box with the highest confidence score. This box is treated as the current best prediction. Then, it compares this box with the remaining boxes. If another box overlaps too much with the selected box, it is considered a duplicate and is removed. The amount of overlap is usually measured by IOU, which stands for intersection over union. IOU compares the area of overlap between two boxes with the area of their union. If the IOU is high, the two boxes are likely to describe the same object. After suppressing highly overlapping boxes, NMS moves to the next highest confidence box and repeats the same process. It continues until there are no more boxes to process. The result is shown on the right. Instead of many overlapping boxes, we now have one clean box for the dog and one clean box for the cat. The important point is that NMS does not improve the neural network itself. It is a decision rule applied after prediction. But without NMS, the final detection output would usually be much less clean and much harder to use in robotics or other downstream applications. So far, we have discussed object detection and segmentation, which operate in a 2D image space. But as you know, our robots live and operate in a 3D physical world. Drawing a bounding box around a carton of milk is great for knowing what is in front of you, but is it enough to actually pick it up? To grasp and manipulate objects precisely, the robot needs to know exactly how the object is positioned and rotated in the 3D space. This is what we call 3D object pose estimation. Object pose estimation predicts the exact 3D position and 3D orientation of a target object from our visual observations. For the input, we can use various types of visual data, such as a standard RGB image, an RGBD image with depth information, stereo images, or even multi-view images. And the output we get from this algorithm is the 6D object pose. Understanding this 6D pose is absolutely critical because robots rely on the spatial information to interact with their surroundings safely and accurately. Let us do a quick recap on how we represent this pose mathematically as a 3D transformation. A 6D object pose consists of two main components. The first one is translation, which tells us the object's position in 3D space. We represent this as a 3D translation vector denoted as T in real coordinate space R3. The second component is rotation, which defines the object's orientation. We represent this as a 3x3 rotation matrix denoted as R in the special orthogonal group SO3. Together, this pose specifies the position and orientation of the target object's local frame with respect to our reference frame. We combine the rotation matrix and the translation vector to form a single 4x4 transformation matrix. This matrix belongs to the special Euclidean group SE3. As you can see in the matrix equation here, the top left 3x3 block is the rotation, and the rightmost column holds the translation. This compact representation allows us to easily map any point from the object's coordinate frame directly into the camera or world frame. Now, why is this matrix representation so useful? Because in robotics, we rarely deal with just one single reference frame. We have the camera frame, the robot's base frame, the end effector frame, and the object frame. To figure out where the object is relative to the robot's base, we use the composition of transformations. A transformation can be mathematically composed through intermediate coordinate frames. The rule is simple. If we know the pose of frame B with respect to frame A and the pose of frame C with respect to frame B, we can easily obtain the pose of frame C with respect to frame A. You simply multiply the transformation matrices together. Let us look at a real robot example. Your vision algorithm gives you the object's pose relative to the camera, which is camera T object. But to command the robot arm to grab it, you need the object's pose in the robot's base frame. So what do? You take the transformation from the robot base to the camera and multiply it by the transformation from the camera to the object. This matrix multiplication chains the frames together, giving you the final target pose in the base frame, so your robot can successfully plan its manipulation. Now let us briefly review perspective endpoint, usually called PNP. PNP is a classical algorithm for estimating object pose from geometric correspondences. The goal is to estimate the 3D pose of an object in the camera coordinate frame. The input consists of three things. First, we need known 3D object points. These are points defined on the object model, such as corners or key points. Second, we need the corresponding 2D image key points. These are the locations where those 3D points appear in the camera image. Third, we need the camera intrinsic matrix, K, which describes the camera parameters, such as focal length and principal point. Given these inputs, PNP estimates the rotation R and translation T. Together, R and T define the transformation from the object coordinate frame to the camera coordinate frame. In homogeneous form, this becomes a 4x4 transformation matrix. The projection equation describes how a 3D point is mapped to a 2D image point. First, the 3D object point is transformed into the camera coordinate frame using R and T. Then, the camera intrinsic matrix projects that 3D point onto the image plane. Because camera projection is defined up to scale, we use the scale value S in the equation. In practice, PNP solves an optimization problem. It tries to find the pose that makes the projected 3D points match the observed 2D key points as closely as possible. In other words, it minimizes the reprojection error. This is why PNP is very useful in robotics. If a vision model can detect 2D key points of an object, and if we already know the corresponding 3D key points on that object, then PNP can convert those correspondences into a 6D pose. So YOLO can be used to detect key points, and PNP can then estimate the object pose. This connection between learning-based perception and geometric pose estimation is a powerful idea in robot vision. All right, now let's move on to Aruko marker-based pose estimation. In this approach, we use specially designed markers called Aruko markers to estimate the pose of an object very accurately. The process consists of two main steps. First, we detect the marker in the input image. This involves several stages such as adaptive thresholding, square detection, and marker validation. At the end of this step, we obtain precise two-dimensional corner coordinates of the marker. Second, we combine these detected 2D corners with the known 3D geometry of the marker. Using this information, we apply the PNP algorithm to estimate the transformation between the camera and the object. The final output is a 4x4 transformation matrix, which represents the full 3D pose, including both rotation and translation. This method is very reliable because the geometry of the marker is known in advance. Now let's look at how YOLO can be used for pose estimation. Unlike Aruko markers, this approach does not rely on predefined markers. Instead, it uses a neural network to predict key points directly from the image. In the first step, the model takes an RGB image as input and predicts the two-dimensional coordinates of key points on the object. These key points are usually predefined points, such as corners or specific landmarks of the object. In the second step, we use these predicted 2D key points along with their corresponding 3D coordinates. Then once again, we apply the PNP algorithm. This allows us to compute the full 3D transformation from the camera to the object. So in summary, YOLO provides the key points and PNP converts them into a full pose. This combination enables marker-free pose estimation, which is very useful in real-world scenarios. Now let's see how we can run YOLO in real time with a robot using ROS2. The first step is to create a package in your ROS workspace. You navigate to the source directory and create a new package called YOLO Detector. This package will include the necessary dependencies, such as RCLPy. The second step is to prepare the required files. You need to download and organize folders such as Launch, YOLO Detector, and Checkpoints. Most importantly, you need your trained YOLO model file, typically named something like best.pth. This file contains the learned weights that will be used for inference. At this stage, your ROS package structure should be properly set up and ready for building. Next, we build and run the YOLO package. First, we build the package using the Culkin build command. Make sure to include the appropriate build options for performance optimization. After building, don't forget to source the workspace. This step is important so that ROS can recognize the newly built package. Then we launch the YOLO node using a launch file. Depending on your task, you can choose either detection or pose estimation mode. Once the system is running, YOLO will process incoming images in real time and output detection or pose results. As you can see in the examples, this enables both object detection and pose estimation directly on a robot system. This is a key step toward integrating computer vision into real-world robotic applications. Now, let's introduce a more advanced method called foundation pose. This is a recent approach proposed in CVPR 2024. Foundation pose aims to unify 6D pose estimation and tracking, especially for novel objects. What makes this method interesting is that it can work even on objects that the model has never seen before. This is a major step forward compared to traditional methods that require training on specific objects. In the following slides, we will explore how this method works in more detail. Let's take a closer look at the problem setup of foundation pose. It supports zero-shot 6D pose estimation and tracking. This means the model can handle new objects without any fine-tuning. There are two main input setups. The first is model-based. In this case, we provide a 3D CAD model of the target object. The second is model-free. Here, instead of a CAD model, we only provide a few reference images. These images are used to build an internal representation of the object. Next, there are two inference modes. The first is pose estimation, where the system initializes and estimates the pose from scratch. The second is pose tracking, where the system refines the pose over time using information from previous frames. This flexibility makes foundation pose very powerful in dynamic environments. Now let's go through the overall pipeline of foundation pose. The first step is initialization. Here, we first detect the object's bounding box using a standard two-dimensional detector. Then, we estimate an initial three-dimensional position using depth information. After that, the system generates multiple pose hypotheses by sampling different viewpoints around the object. The second step is pose refinement. For each hypothesis, the system compares the observed image with a rendered image of the object. These inputs are processed by a transformer-based network. The network predicts small updates in translation and rotation, gradually refining the pose. Through this iterative process, the pose becomes more and more accurate. Finally, we move to the last step, which is pose selection. After refining multiple pose hypotheses, the system needs to choose the best one. To do this, it uses a hierarchical self-attention mechanism. This allows the model to consider global context across all candidates. The hypothesis with the highest score is selected as the final pose. Now, in pose tracking mode, the process is simplified. We skip the initialization selection steps. Instead, we directly refine the pose using the result from the previous frame. This makes tracking much faster and more efficient for real-time applications. Here are the references used in this lecture. They include key papers such as FastRCNN, various versions of YAOLO, and recent survey papers. Additionally, we included works on pose estimation such as center pose and foundation pose. If you're interested in deeper study, I highly recommend going through these papers. They will give you a much better understanding of both the theory and practical implementations. This is the end of today's lecture. If you have any questions, please post them on KLMS Q&A. Thank you for your attention.